So if we're looking at the following balanced reaction, we have 4 moles of aluminum, 3 moles of our diatomic oxygen, producing 2 moles of our aluminum oxide. So what is the ratio of aluminum atoms to oxygen molecules needed for this equation? So when we're looking at this, going back to prior lessons, we're looking at the coefficients that are out in front of each of the elements. So reactions, we're going to be using table I, gives us the ratio of reactants and products and the energy for a given set of reactions. So what we're going to be doing is comparing these moles to that delta H value that is produced. So when we're looking at a sample problem, the first one says how much energy is produced when 2 moles of oxygen are consumed in the production of NO. So the first thing you need to do is find where oxygen and nitrogen are combining to produce our nitrogen oxide. So if you're looking at table I, it's about half of the way down. You have nitrogen and oxygen synthesizing. You have N2 plus our O2 producing or yielding our 2NO. And by looking at those, now you can figure out what is the relationship between those. So in this case, it says how much energy is produced when 2 moles. Well, when we have 1 mole, we know that we are producing 182.6 kilojoules. Now, setting that proportionate to our new ratio, now we have 2 moles, and we're going to just solve for x. So based off of solving for x, you're going to cross multiply, and since it is just going to be double that value. Looking at our next example here, it says how much energy is needed if 10 moles of carbon are consumed to produce C2H4. So looking at that, you're going to be looking at, again, table I, trying to find out where carbon are consumed to produce C2H4. So looking at the C2H4 piece, you're about a little over halfway down the page, and you can see that carbon and hydrogen are synthesizing to produce C2H4. So in this case, we have a ratio of 2 moles of carbon producing the amount of 52.4 kilojoules, and we're going to put that in proportion now to 10 and put that over x to figure out that. So we're going to have 2x equals 524, and then divide that by 2. So now you have x equals about 262 kilojoules is your answer. Looking at our last sample question here, it says if 5.3 moles of sodium hydroxide is dissolved in water, how many moles of energy are released? So when we're looking at those, we need to find that equation off table I. So sodium hydroxide, remember, is NaOH, is dissolved in water, so we're just dissolving that, now becoming aqueous, so it's dissociated. And you're looking about 6 from the bottom there. And as you look from 6 to the bottom, we know that 1 mole of our NaOH is present, and the amount of heat that is emitted from there is negative 44.51 kilojoules. Now, based off of that, I'm changing to 5.3 moles of sodium hydroxide. So I'm going to put 5.3 over x and then solve for x. Cross multiplying there, you're going to end up with x equaling negative 235 kilojoules of energy. So going into that, just a quick little couple things that you're going to use from table I in order to solve for those equations. Next, we're going to be looking at thermodynamics.